Alright, this is a talk on some of the advanced features of PostgreSQL. My name is David Blewett. I'm a senior developer at 6 Feet Up. Alright, go ahead. Kind of an overview of what we'll be looking at are some of the new features coming in Postgres 9.2. Some of the existing features that some people might not have had experience with, and some admin related bits. Okay, Postgres 9.2 is in RC release candidate status. I think RC1 came out just earlier this week. They have basically an annual development cycle, so each year a new major version comes out. For Postgres, the major version is the second digit, so anytime you're talking about 9.0, 9.1, 9.2, those are all major versions that the developers take pretty seriously, so you have to usually do a complete dump and reload of your database if you want to take advantage of the new version. One of the big features coming is an in-core JSON type. It's been in development for a while. It was initially scheduled for 9.1, but there were a few issues that didn't get resolved in time for the release, so it got pushed to 9.2. Another new type are range types. A large performance increase can be seen with index-only scans. Those basically allow you to create an index of different columns, and if your query only pulls those columns, it can be satisfied by looking up the data from the index and doesn't have to find the records in the database heap, which can be a lot faster. With the expense of if you're updating the data a lot, the index has to be updated frequently, but if it's mostly read-only and you only have a few columns that you need to look at, it can be a large speed boost. And then also they enhanced the replication to be able to cascade so that you can daisy chain replication servers instead of every replication slave having to contact a single master. You can now farm it out so that you don't have as much of a performance drain on the master. Alright, we'll look at the new types in a little bit more depth. The JSON type is pretty interesting. Previous versions of Postgres had an HStore type, which was very similar to JSON, basically a key value type. It allowed you to have an unstructured schema for that particular value, so you could have any number of keys and values. One large limitation of it, though, is that you could not nest it, so you could not have a value be another set of HStore records. The JSON type is a full implementation of the RFC, which allows you to have deeply nested objects. You can have all the core JavaScript types, booleans, strings, arrays. What it's best for is if you aren't able to define a specific schema ahead of time for a set of data, such as a member profile, where some sites might need different bits of profile information, things like that. You can use this type and be able to store specific information for a member without having to have the specific columns in the table. It's also good if you're passing data around into database functions. As I mentioned before, the HStore type doesn't nest, and other methods of having the schema of the member profile be defined at runtime instead of when the database is created are pretty complicated. The entity attribute value is a pretty common paradigm where you store basically keys and values in a single table. But if you want to pull all the information for a particular record into a single row, it can be pretty complicated, requiring several different queries to pull it all into a single value. Whereas with the JSON type, it's just a single field in the table. Because this is the first version that this type is appearing in, there are some teething issues. there isn't as much as rich of a feature set of being able to integrate the JSON data with different aspects of the system. So if you really want to take advantage of it to index values, you have to rely on third-party procedural languages. A popular choice is Google's V8. There is a V8 procedural language which allows you to write functions directly in JavaScript and be able to parse the JSON data. We'll go ahead and take a look at using the type. Here I'm just creating a members table with a single column. If you have some fields that you know in advance you want every member to have, you can go ahead and add those here, but we're assuming that it's going to be completely dynamic, so each member might have different fields. So here we just insert the JSON structure into a single record. Now if we want to be able to pull specific fields from that, we, like I said before, need to rely on a third-party procedural language. Here we'll create the function to extract a specific key from the JSON structure. So you pass it the key name and then the JSON data, and it will parse the data into an object and then extract your specific key. And then we take advantage of Postgres's casting feature so that the data type that it returns is numeric. So it will be able to cast the JSON numeric type to Postgres's native numeric type. And then we can just create an index on extracting the age value using this new getNumeric function. This will just store Postgres's native numeric type in the index. So now when we want to query and take advantage of this index, we need to use the same method in the query. So we use the getNumeric on the profile column, pass it the age key, and then our criteria, and then Postgres will be able to take advantage of the index that we created before. As the table is updated, Postgres will keep it up to date for you automatically. You don't have to do anything. There are some maintenance tasks. You can reindex or cluster the table on the value of that index, but those aren't uncommon needs. The common case of just inserting new data or updating values, Postgres will call this function every time it gets updated. Were there any questions about using this type? Postgres has a very rich type system, and until now, if you wanted to be able to pass in custom fields, it would either require multiple variables to a function or defining a custom type. Using JSON, you can get around a lot of that and just have your function accept a JSON variable, and then in your function you'll be able to extract whatever bits you would need. Then whatever language your function was written in would just need to be able to parse out that data. There are several different procedural languages. I mentioned V8 for JavaScript, Python you can use, Perl, and then you would just use those languages facilities for parsing out the JSON. At the end of the presentation there are several links to some more in-depth uses of JSON. Next type are range types. This is very useful if you have, say, a calendar application where you would like to have repeating events. You don't have to, say, create a record for every single date that you would like the event to repeat. You can just say a specific date range starting on one date and ending at another. You can specify if it includes or excludes the endpoints as well. There are several built-in ranges for integers, numeric values, timestamps, or dates. And you can also define your own custom range types, passing in the different comparison functions. Those have to be written in C, I believe. So we'll have a couple examples of using it. So you can define a during timestamp range and pass it the values that the room would be in use. And then you can do comparisons on if a specific value is inside that range or you can find the upper or lower bounds or the intersection of different ranges. So it's a pretty useful feature. The previous pattern that I alluded to earlier about having to store multiple rows for every single date in that range could be pretty cumbersome. So this is a very elegant design. Alright, moving on to some of the existing features that might not get as much use as the usual SQL data types. We'll talk about full text search, window functions, and foreign data wrappers. Postgres's full text search is pretty flexible. The default is if you create a new table and want to index a text value, is to use the current system locale, or you can create your own text search configuration, passing it different encoding parameters, custom dictionaries, different stemmers, things like that. The core types that Postgres uses to represent the different aspects of the search are a TS vector and a TS query. A TS vector would represent the data that you would like to search. Basically, it will use the configured text search settings for the different stemmers and dictionaries and things, and use that to parse out the data that you're giving it into different lexemes. So it will keep a sorted list of distinct lexemes. And then the TS query is what you would use to compare against that TS vector. You can give it different words and then combine Boolean operators to get at different aspects of the full text. You can either generate these values on the fly in a query, or you can store them alongside the data that you're indexing. The usual pattern is to add an additional column to your table of type TS vector so that Postgres will keep that up to date whenever you insert or update the table and calculate all the different lexemes so that doesn't have to be done every time you do a query. Here's a simple example. So Postgres provides the toTSVector function that basically takes your text and then calculates the different lexemes. So you can pass it any text that you would like. You can combine different fields from your table, or different calculations based on the fields in the table. Then you would use the @@ operator and then the toTSQuery function to parse the text and Boolean operators that you would like to search for. So this would basically look for any records that have the words create and table in either the title or the body. Postgres provides different functions to sort by relevance or different weightings, but in this case it just sorts by the last modification date. So it would find all of the records that match your query and then sort them by the last modification date and return the last 10. Here's a little bit more involved example where we're going to create a column to add to the table to store the parsed representation of the text you want to search, create a trigger to keep that column up to date, create an index on the column, and then basically the same query we had before. So we add our text searchable index column. You can use any column name. It just needs to be of the TS vector type. And then we'll go ahead and update that column to the parsed representation that we want to be able to search, passing it in the title and the body. And then we want to make sure we create a trigger to keep that column up to date whenever we update the underlying table. So if new records are inserted or a record's title or body changes, Postgres will automatically update the parsed representation. And then we add an index on the column using the GIN index engine, which basically, while the query at the bottom of the screen will work, it might take a significant amount of time to find whatever records you're looking for. The index will just make that operation much faster. So now instead of having to do the toTSVector calculation inside the query, we just give it the column we want to use and then compare it against the 2TS query version of our search terms. It might be a little bit more complicated than, say, Solr. Bits in Solr, you're defining your schema ahead of time and giving it basically just the name of a function. Once you add the column and the trigger, you don't have to touch this configuration again. You can just give it the column name and whatever query terms you would like to pass to it. There are more advanced features, like I mentioned before. So let me go back to this example. In the update statement and the trigger, we tell it we want to index the title and the body. You can give different weights to the different fields that you're going to include in the TS vector. This way, when you do a comparison later on, if search terms appear in, say, the title, you can weight those more, and those will then bubble up to the top of your result set. You can also do custom highlighting. So if you pass the query terms, you can pass the results through your highlighting function. That particular step can be time-consuming because it has to run through the entire text in the column and highlight your search terms. So in this example, if we're doing a limit by limit 10, it still has to calculate the highlighted terms for all those records that will be returned. There's also query rewriting, so that if you take this 2TS query value, you can apply rules to add additional values to the query. And then we have this example of the trigger that keeps the column up to date automatically. All right, the next major feature are window functions. This is the basis for what are called recursive queries. They're not truly recursive. They basically iterate over a list of records that are returned by an underlying query. So let's take a look at here. We create a simple employee table with the employee's identifier and then another column which is their immediate supervisor. And then we'll insert different values into the table representing a basic organizational structure. And then in this query, we're going to, at the very beginning, we define the source for all the iterations that will succeed it. So we're going to select all the values from the table where the boss ID is null, and then we're going to iterate through the employee table and find every record that has a boss ID assigned to it, accumulate that into the employee ID into an array, and then finally we'll format the data. So it might be a little bit complicated, but here we can look at the output that it gives. So since the number one employee does not have a boss, he's rooted at the top, and then we descend the organizational structure with the employee ID of 2, then supervises all of the records underneath, and then so on down the tree. Previous iterations of this algorithm were pretty complicated. Techniques such as nested sets, which basically store an ID for every single leaf in the tree. That can be pretty expensive if you have a table that is updated heavily, because as new nodes are added or moved to different parts of the tree or deleted, you have to then recalculate every single object in the tree, recalculate their position. Whereas in this case, it's just calculated dynamically when you do the query. This is an existing feature. It's been around since, I think, 8.4, which is I want to say 2 years old now. It's a very elegant system. I think version 9.2 extends, or maybe it was 9.1 even, extends this ability so that you can do complete data manipulation on the records that are returned by the recursive query. All right, the final topic is foreign data wrappers. This is a a concept that basically lets you integrate a huge variety of external data sources and access them as native tables in Postgres, so that you can do joins or use regular SQL syntax against, say, a flat file, web services, other SQL databases, NoSQL, such as Couch or Mongo. The beauty of this is that you are taking advantage of Postgres's powerful query language and query planner, but you don't have to store that data inside of Postgres. It's an extremely flexible design so that you can import the data from the external source or just include it and be able to integrate it with the data that's already stored in Postgres. The low-lying API that powers this requires a C interface, so the external databases, you would have to write your own wrapper that would integrate with their C interface. Luckily, there's a project that's called Multicorn that is basically a Python abstraction layer where it provides the C bindings for Postgres to use, and then it will use the Python procedural language to make available any of, say, the SQL Alchemy data providers or any of the other DB API providers, or you can write it a simple wrapper inside Python. You don't have to drop down to the C layer. Multicorn will provide the interface back to Postgres. In the talk, I'll have some links of some examples for that. Here's a simple example using the Twitter foreign data wrapper. The bottom is the query. So it will provide the Twitter table, and then you can pass it a query for the PostgreSQL hashtag, and then it will use Twitter's web services API and pull back all those results. And you would be able to use that to join against any data that you might have in your system or import it into native Postgres tables. All right, so as I mentioned before, there's a lot of talk of the JSON type and some of the advantages that it will provide. So most of these links are related to that. Some detailed steps for being able to create indexes inside of Postgres based on that type and how to use it internally in your system. And then there are some examples at the bottom of the window functions that on the Postgres wiki, the Mandelbrot set, you can have a graphical representation of the Mandelbrot set that Postgres can calculate for you. It's pretty interesting. All right. Thanks for listening.